Hello everyone. I'm going to show you a video of the Wonderland model. So we're here in the Lecture 8 directory. All these files will be uploaded into our folder. So I'm going to open the Wonderland model. Just to give you an idea of what we're looking at. And so let's take a look at this. And I think the first thing that you'll appreciate when you look at this model is that it looks very, very densely packed. And this is one of the comments that I made in the lecture previously, is that I think this model's got way too many parameters for what it does, and I'll come back to this in a second. But let's give you the typical rundown of the model. First, identify the stocks. We have the four major stocks: population right here. Okay, the output per capita. This is Y. Population is X. Output per capita. The natural capita. This is Z. And the pollution per unit output, which is P. Okay, so let's take a look at how each of these stocks is assembled from the Fluxus point of view. So population has got two stocks: births and deaths. Okay, and we've seen this pattern repeating itself before. If we take quickly look at the equations, if we look at population, it's basically births minus deaths. It's got an initial value of 1. It's got the units of people, okay, and this this model's got the just to translate, because the model's got so many variables. It is useful to have in the comment section what parts of the model correspond, or which variables of the model correspond to the variables in the paper. Okay, so I think that's important. So if you look at the births, you'll see that the birth it's composed of the product of population times the birth rate, okay, in people per year, and the birth rate it's essentially one of the equations in the paper. So it's got it's got the coefficients, like a beta 1 and the beta 2, the exponential function. So these are the functions that are presented in the paper. Okay, so essentially this group of variables, I'm not going to go through all of them. I welcome you to do this, one by one. If you just click on any of these, you'll find the value, and this is the variable beta in the model. So if you look at the comments section, you will see what variable in the model corresponds to what variable in the paper. I think that's useful because, as you saw, this model's got 20 parameters, so it's a little bit difficult to keep track of who is who. So this group of parameters here refers to the births in the population. Now the death rate, the deaths are driven by a death rate, and the death rate is driven by this group of parameters here. Okay, so if you click on the death rate equation, you will see essentially that the death rate in units of 1 per year, it's a product of two variables: normal death rate and environmental effects of causing death. And then you can see there's two products. This here, it's the delta 3 component of the death equation, and this here is the delta 1 and delta 2 component of the equation. Okay, you can see again that I keep coming back to this in simulating or formulating a simple death relationship. There's way too many parameters. Another thing that this model does very effectively is the use, and I think it's caused by this density of parameters, the use of different colors to associate the parameters that interact mainly with the stock variable. So, for example, in this case, all the population parameters and related equations are in purple, and so on. So I'm going to move on to the next variable, the output per capita. Okay, and the output per capita is driven by the output net exchange rate. It's got units of dollars per person per year. Okay, so this is essentially dollars per year generated in the system per unit population per unit person. It's got an initial value of 1, like variable in the model, and this is This is the variable y of t. So that essentially is driven by this in the red variables. Okay, so this is the sort of the economic model in the system, and then you have the output rate, which is the product of the output per capita, which is y, times the output growth rate. If you look at the output growth rate, then you get you get the equation that's in the paper. Okay, it's a growth rate minus a growth rate plus. So this is I believe this is like a gamma, and then gamma minus gamma plus eta times 1 minus z to the exponent, and all those parameters are defined here. Okay, and if you click on any of these parameters that are given, you'll find this is gamma. So, and it's a little comment there just to aid in the tracking down of the parameters, which is a challenge with this model. Okay. We can move on to the next variable, which is the natural capital, right here. And you click there, you get again, and this is it's got units of, actually this model has got units of natural capital units, NKUs, which is a fictitious unit to deal with natural capital. And this is variable z, and it's got an initial value of 1. Okay, and it's driven by here by a net change rate, and this net change rate is pretty involved. It's this is the logistic equation for here for capital. And one of the things that I mentioned in the presentation is that and we'll see some of the results is that in this case, and I think that's probably the reason, although it's not stated explicitly anywhere, but one of the reasons why they call this the Wonderland model is because in this model nature regenerates itself, but there's really no consumption of nature, or direct consumption of nature as we had in the handy model and other simpler models that we've seen. And I think that's part of the reason why the nature stock, the natural capital stock, really varies very little in these simulations, is because there's no mechanism to consume nature. So I think the effect, so there is an effect of pollution in reducing the regeneration rate, but there's really no consumption, direct consumption, and I think that's an issue. But it might be why I call it the Wonderland model. It's a world of wonder where nature just regenerates itself, and that nature is plentiful. So it's that's probably the reason why it's called like that. Although, like I said, I haven't seen the naming anywhere. So anyway, with that comment aside, so essentially what you have is natural capital being generated or regenerated through these green variables here, properly colored for nature, so you have the cleansing flow, and you have the pollution flow. So those are the two counteracting, and of course the pollution flow provides a link to the next stock, which is the pollution stock. But essentially between these two, so if you go to the regeneration rate, what you're going to see is that there's that this is the exponential equation that appears in the paper, and if you look at the way the nature is regenerated, it's through the counteracting difference of these two. The cleansing flow minus the pollution flow provide a regeneration rate. If we look at that again, you can see that the difference, the cleansing flow minus the net pollution flow, appears there. But again, they appear in terms of attenuating the nature regeneration, not really of consuming nature, which I would have liked to see. So so that is the natural capital stock. And then lastly, we go into the pollution output, and then the pollution output, of course, it's got a series of variables that affect not only pollution but also, the natural capital, and indirectly a little bit the per capita output. So if you look at the pollution stock, what you're going to see is that it's it's driven by a pollution change rate, which we'll talk about in a second. It's got an initial value of 1, and this is P of T. And it's got units of pollution units, PUs, per dollar per capital produced, per unit capital produced. This the intensity change rate, the change rate of pollution is essentially driven by a single coefficient, and that coefficient, it's here. This is pollution change rate, which is chi in the model. Okay, the variable chi in the model, and that's the value that's given. It's negative because pollution essentially decays as pollution gets generated, which is another assumption or another variable that I found a little bit at least questionable. So and I made I made those comments in the presentation. But then pollution drives pollution output, which affects the nature regeneration rate. And there's again a series of coefficients that appear here, like the abatement coefficient, kappa, which is a value of 2, and the units are all there, and you can see how the information flows. So this model is fairly interesting to in terms of, and I highly recommend that you kind of go through the model in a lot of detail and understand how the variables connect. So from a model structuring point of view, I enjoyed looking at this model. This model, by the way, was based on the original reference by Warren Sanderson, which is provided in the readings for this lecture. But this model was replicated in VENSIM by the folks at Ventana Systems, by Tom Fitteman, and I made some friendly changes. I moved some things around just to make them a little bit more user-friendly, at least for me. But the one thing you'll see is that the model's got 20 parameters. It's got a myriad of functions defined with these parameters. For the most part, the results are very insensitive to a lot of these parameters. So I'm not sure that, I'm pretty sure that you can achieve the same, some of the same results or capture the same complexity in the system by using less parameters. If you make a quick run, and I have the model set up here, so I'm going to run it and have a few graphs set up in the, let's say yes, and if you run the model, let's go to the right, and you'll see some results. Population increasing from 1 to nearly 4, population units, the output per capita, Y shoots up exponentially, so there's if you look at the natural capital stays at 1. So again, there's no depletion here, and I think that this is part of the reason why the output can grow so quickly. It's because there's plenty of natural capital, and then pollution drops over time. So I found this combination of parameters a little bit how would I say, unrealistic, if I want to be generous. But I encourage you to play with the model. I tried a few things, like for example, if you pull down, and maybe we can do that quickly here. If we pull down the availability of natural capital, so instead of starting with a fully stocked nature, I start with half. Okay. Half, say okay, let's change this to scenario 2 and run it again. Okay, this nice thing about VENSIM is that you can run this very quickly, and you can see again, and this is the one that sort of got me thinking about the multiple parameters. See, if you look at what's happening here, scenario 2 is the blue and scenario 1 is the red. So in scenario 2, population grows a little bit more. Okay, which I found a little bit surprising, but it's probably all right. Production stayed more or less the same, because really natural capital, you start at 50%, and it shoots up to its carrying capacity very quickly. So there's an inherent regeneration that's implicit here that I don't think is realistic. And again, I think that's driven by the fact that nature is really not being consumed. So even if you start with little nature, it shoots up. And again, this pollution dropping, I don't like it either. So I'm going to try a third scenario on you, since I have you, on the edge of your seats. I'm going to try scenario 3. And if for some reason these graphs are not moving properly, but I'm going to do 2 things here. Well, I'm actually do one thing. I'm going to leave the natural capital as is, and I'm going to change the pollution sign from negative to positive, meaning that now pollution is not going to decrease over time necessarily. Okay, it'll probably be produced over time. So we're going to run this as scenario 3. We run it again. This is one of the nice things of VENSIM, is that you can start looking at these things. And so first of all, pollution grows over time, okay, before a decrease. It makes sense that pollution grows over time if population is growing over time and production is growing over time. I just don't see how pollution, and I think there's some very and I probably pro-economic growth, anti-environment assumptions embedded in the model explicitly. But again, you see how this natural capital, even with this, it shoots up. Very, very weird. Again, population doesn't change much. You've got plenty of natural capital. This drives production up, and pollution, even with pollution growing, there's not a whole lot of an effect. So pollution here doesn't have a whole lot of an effect on nature and production. So I think it's not really very realistic. I want to do a 4th scenario. I think I tried this one before, in which I'm going to really start with a low value of natural capital. So I'm going to start with 10% of carrying capacity. Okay, so I'm going to do that. I'm going to run this baby, and runs very quickly. I go again, and now we start seeing a little bit of a different behavior. Again, pollution growing on blue. People growing more, actually. There's more growth in this case. And the output per capita still going up. It's really an economist's model, I should say. Nature takes a little bit longer to regenerate, but it does regenerate nonetheless. So it's different. It's difficult to envision with a model like this a collapsing scenario, and I don't think you can get one. Or maybe if you tweak the parameters. So I'm gonna ask you to really play with this, tweak it. Try to push parameters up and down, see what you get. Maybe you can try one of these. These synthetic simulations. If you click here, the way I set it up. Let me say no here. If you run a scenario 5, if you wish, let me just change this to scenario 5. And if you do a synthetic simulation here, you might be able to tweak. So now you have all these knobs. So I encourage you to really try to push these knobs and see what the results are on the graphs on the right. And please report any insight back on our Facebook page. I want to see some discussion. I'd love to see any insights on this. My own assessment is that it's really it's a model. I shouldn't say this. I'll say this half jokingly. It's essentially an economist's dream model. Nature regenerates itself. It can produce forever. This allows us to grow population forever. No collapse. So anyway. That's my comment for this model. I hope you enjoy the the model and the presentation.